Ayubowan children, and a very warm welcome to Study Hub Sri Lanka. Today, we're going to tackle one of the most important topics for your GCE A-level physics paper, coplanar forces in motion. Now, this is Unit 1, and trust me, getting this right is absolutely crucial for your success in mechanics. So, let's get started.
So, how are we going to do this? Well, I've broken it down into 5 simple steps for you. Think of this as our roadmap. We're going to start with the basic tools, then meet the different forces, see how they behave when things are standing still, then see what happens when they start to move, and finally, we'll bring it all together with a master technique. Nice and logical, right?
Okay, first things first. Step 1, the basic toolkit. You see, before we can solve any of these big problems, we have to be comfortable with our main tool. And in mechanics, our main tool is the vector.
Now have a look at this. You've got a force, let's call it Q, pulling at an angle. The most important skill you need is to be able to split this one diagonal force into 2 simpler parts, one that pulls purely sideways, horizontally, and one that pulls purely upwards, vertically. And the rule is simple, children. The part that is next to the angle, the adjacent component, always gets the cos, so it's Q cos theta. The part that is opposite the angle gets the sine, so that's Q sine theta. This is your bread and butter for mechanics, so make sure you've got it.
So if we can break a force down, it makes sense we can build it back up, right? It works both ways. Imagine you have a bunch of different forces all pulling on one point. We can combine them all into one single force that we call the resultant force. This resultant, R, tells you the whole story. If R is 0, it means all the forces have canceled each other out, and the particle stays perfectly still. But if R is not 0, the particle is going to accelerate, and it'll go in the exact direction of that resultant force.
All right, so we've got our tools. Now let's meet the players. Step 2 is all about the actual forces you'll be working with. Think of them as the main characters in all of our mechanics problems.
Okay, welcome to our little zoo of forces. You're going to see these 4 characters everywhere. First up, we have weight. Simple. It always pulls straight down towards the center of the Earth. No exceptions. Then there's the normal reaction. That's the surface pushing back, and it's always at a 90-degree angle to the surface. Next is tension, which is the pull you feel in a string or a cable. And finally, the tricky one, friction, the force that always tries to stop things from moving. You absolutely have to be able to spot and draw these 4.
Now, a quick little detail here, but it's a common trick in exams. See the string on the left? A string can only pull, right? You can't push with a rope. That's what we call tension. But look at the rod on the right. Because it's rigid, you can pull it, that's tension, or you can push on it, you can squash it. And we call that compression or sometimes thrust. It's a small difference in the words, but a big difference in the physics.
Right, let's talk about friction. Now, pay close attention here because this is where many students get a bit confused. The thing about friction is it's not just one fixed number. It's clever. It actually changes its strength depending on what the object is doing. So let's look at the 3 main situations one by one. Okay, imagine you're trying to push a heavy cupboard. First, you push gently. That's stage 1, static friction. The friction just pushes back with the exact same force you are applying, F equals P, so nothing moves. Then you push harder and harder until you feel it's just about to budge. That's the breaking point, stage 2. We call it limiting equilibrium. At this point, friction is at its absolute maximum value, and we have a formula for that. F max equals mu times R. The second it starts sliding, we're in stage 3, kinetic motion. And here's the cool part. Once it's moving, the friction actually gets a tiny bit weaker. It drops and then stays at a constant value while it slides. One last thing before we move on. We know weight pulls down, but from where exactly does it pull? Well, for any object, we pretend its entire weight acts from a single special point. We call it the center of gravity. Now, for nice, uniform shapes like a rectangle or a circle, it's easy. It's right in the geometric center. But for more complex shapes like a triangle or something made of a few parts stuck together, we have to use some specific rules to find that exact point.
Okay, so we've got our tools and we've met our forces. Now for the fun part. Let's see how they all interact with each other. Step 3 is where we look at situations where everything is perfectly still, perfectly balanced. This is a big topic called static equilibrium.
To talk about balance, we need to talk about turning. Think about using a spanner to turn a nut. That turning effect is what we call a moment, and the formula is super simple. It's just the force you apply multiplied by the perpendicular distance from the pivot point or the center of the nut. And we just have a little convention. If it tries to turn anti-clockwise, we call it a positive moment. If it tries to turn clockwise, we call it a negative moment. That's all there is to it.
And this slide, this is pure gold, children. For any object that's not moving and not rotating, these three conditions must be true. They are your secret weapons for solving statics problems. Rule number 1, all the forces going right must perfectly balance all the forces going left, so their sum is 0. Rule number 2, all the forces going up must perfectly balance all the forces going down. Their sum is also 0. And rule number 3, about any point you choose, all the clockwise turning effects must perfectly balance all the anti-clockwise turning effects. If these three things are true, that object isn't going anywhere.
Okay, we've mastered things that are still. But let's be honest, physics gets really exciting when things start moving, doesn't it? So what happens when those forces are not balanced? Well, that's what step 4 is all about. Welcome to the world of dynamics.
And here it is, the one, the only, Newton's second law. This is probably the most famous equation in all of physics, and for good reason. It's the engine that drives all motion. It simply says that if you have a resultant force, an unbalanced force, it will cause an object to accelerate. F net equals m times a. You will use this equation again and again and again. It is everything in dynamics.
Now you'll often see problems like this one. Two masses connected by a string over a pulley. It looks complicated, but there's a simple trick. Because they're tied together with one string, they have to move together. This means the acceleration a is the same for both. And the pull of the string, the tension, T, is also the same on both sides. So what do? It's easy. You just look at each mass on its own, apply F equals ma to it, and that gives you two equations to solve together. That's the whole strategy.
Okay, we've come to the final step, step 5. This is the one technique that pulls everything we've learned together. It's the key that unlocks almost any mechanics problem, and it's called the free body diagram.
Just look at the difference here. On the left, you have the real-world situation. It looks messy, right? It's hard to see what's really going on. The secret is to do what you see on the right. You mentally explode the system. You take each part and draw it all by itself, isolated. When you do that, suddenly all the hidden forces, like the pushes and pulls between the blocks, become visible. Once you have this beautiful, clear diagram for each body, applying your F equals ma or your equilibrium rules is an absolute piece of cake.
Whew, that was a lot to take in, I know. So let's put all the most important bits onto one single page for you. This is your exam-ready summary.
And here it is. Think of it like this. Column 1, these are your fundamental tools for splitting up vectors. Column 2, this is your knowledge of friction, knowing which of the three states you're in. And column 3, this is the big decision you have to make for every single problem. Is it balanced and still? Then you use the equilibrium equations, where everything sums to 0. Is it unbalanced and moving? Then you use the big one, F equals ma. Get that decision right at the start, and you're halfway to the correct answer. So, let me leave you with this final piece of advice. Whenever you're stuck on a mechanics problem, just remember this simple process. First, resolve your vectors. Second, isolate the body. Third, solve the system. It's a precise, logical path that will guide you to the right answer every single time.
All right, and that's a wrap for today, children. Thank you so much for joining me. I really hope this session has made mechanics a little bit clearer and a little less scary for you all. We'll be back very, very soon with another lesson to help you with your science subjects.
Hey, before you click away, if you found this helpful, please do us a small favor. Just click that subscribe button for Study Hub Sri Lanka on YouTube, and don't forget to ring the little bell icon. That way you won't miss out on our next lesson. Until then, take care, study well, and I'll see you soon.